All right, hello, I'm Johnny Wyant. I'm working with Tyler Dolan and Michael McLaughlin. For our project, we built a pendulum that will demonstrate conservation of momentum and impulse. So first of all, it will be using the conservation of energy to determine an initial velocity, and then it'll be colliding with another object. Then conservation of momentum will be used to determine a velocity of the two masses together. Then that velocity will be used to determine a height that we will be able to predict that the pendulum will reach. That will be, again, conservation of energy. The collision will be a plastic collision, so energy will be lost. So conservation of energy just by itself cannot be used, so conservation of momentum is required. Our coefficient of emissivity is going to be 0, as our final velocity of both masses will be equal to each other.
Okay, now this is the pendulum we built. It is built out of wood and this metal rod with a magnet at the end of the pendulum. And we will be using these metal weights to demonstrate where it will attach to the magnet, and it will be a plastic collision, as was said. Now, the pendulum will be looped up all the way to be matching this rod. That will be the constant height that we will be starting at, which is about 17 inches, which is 0.432 meters. And then we will release the magnet, causing it to swing back and forth. And we will then use a camera to try to eyeball exactly where on the graph it reached. And then we would do some conversions and find the height. So to demonstrate, I will demonstrate the experiment. And that's about it.
Okay, so we will begin with our conservation of energy. So to determine how fast the pendulum will meet when it gets down to its bottom point and picks up the magnet. So our equation for this is potential energy plus kinetic energy will equal the final potential and kinetic energy. So here we have written out the actual equation. So essentially the T2 will equal V2. And we plug in our numbers, and we find here the Vmag with our plugged in values that we calculated with our measurement. So we find our velocity at the bottom of the pendulum to be 2.911 meters per second. So now that's done, we can use the conservation of impulse momentum to find what's going to happen when it picks up the magnet and change its mass. So we start with mass times velocity plus of the magnet plus the mass times velocity of the stationary plate. So that will go to 0, and then when they combine, the masses will add and we'll have a final velocity. You plug in the numbers and it spits out the velocity of the two masses as they are connected, which is 2.329 meters per second. Okay, so we've calculated our velocity after it is connected with the plate. So now we need to use conservation of energy again to determine how high the entire system will go. So again, potential energy plus kinetic energy in will equal potential energy plus kinetic energy out. Or T2 will equal V2, since our datum is set at the top of the experiment. So then we do the math to get this formula here, and then solve for h using the numbers that we've already calculated. So theoretically, our combined magnet and plate should reach 0.277 meters. So then we do the experiment, and we actually get experimental values for our h's. So we took 5 runs of each weight and average them out. That way we get a nice consistent base to judge it by. So here we start with just the magnet, no plates, and then the smallest plate, medium plate, large plate. So then we have to compare these heights to our heights from before to get our experimental percent error. So formula for that, calculated minus experimental divided by calculated times 100 to get a percent. And when worked out, we get, with no weights, 14.8% error. And then with H1, or HM1, we get 21.4% error. And then the other two weights are as follows. As you can see, we averaged around 15% error, so not fantastic, but hey, it's real life, not experiments, or experiment, or theoretical. So the loss due to this, the reason for this percent loss would be friction in the system, inconsistent judgment of release heights, and the non-perfect system of a magnet hitting up a rod.